Kind of starting 10 minutes earlier, more or less. But try to keep it. Thanks for having me, and I'm gonna take the discussion a little bit to other places, and talk about a new architecture for supercomputing that we call it cloud native supercomputing. Um, what does it mean? Why it's important, and so forth. Here we go. So if we look on AI or look on supercomputing, essentially AI or usage of HPCs is going everywhere. There is increase in application that requires an HPC infrastructures or supercomputing infrastructures. Increase in companies that requires to run those applications. Increase in users and so forth. And therefore, there is a great need to enable supercomputing as a service, actually. Same as electricity has become a service, and if you're buying electric device, you don't need to build your own power plant. Computing has become a service, and that's thanks for cloud infrastructure, cloud computing. But now we look on HPC and supercomputing. And the next stage is to enable supercomputing as a service. So more people can utilize supercomputing infrastructure being built, as most people cannot afford building one for themselves. And that's what we call cloud native supercomputing. Cloud native supercomputing is not necessarily a virtualized environment. It can definitely be bare metal infrastructure. But we need to combine here several things. We need to combine in this new architecture the ability to enable multi-tenant, to enable isolation and security between users as needed, while maintaining bare metal performance. So enabling multi-tenant isolation with bare metal performance, regardless if it's virtualized or not virtualized. And obviously, when we're looking on supercomputing infrastructure, mostly it's not virtualized. Beyond of that, as part of better supporting growing amount of users on a shared infrastructure, you also need to bring capabilities such as performance isolation to make sure that one application or one user cannot impact other user application performance and so forth. So that's what sits behind the new architecture that we're calling that cloud native supercomputing. We have announced last year essentially the latest generation of InfiniBand, which is called NVIDIA Quantum 2 InfiniBand platform. That 400 gigabit per second InfiniBand generation is now shipping, is in production and shipping, and start to being the important backbone of multiple AI systems around the world and supercomputer systems around the world. Quantum 2 brought or introduced new capabilities as part of supporting growing amount of users on a supercomputing infrastructure. It brought the capabilities of doing performance isolation on one side, ability to bring tenant isolation on user isolation on the other side, while maintaining bare metal performance. There are other elements such as new in-network computing engines, as the network long ago stopped to become just a pipe that moved data from one side to another side, but definitely on the InfiniBand side of things is becoming actually an element, an active element that take active part in running data algorithms or user-defined algorithms. Other elements, other new elements for precision timing that can be shared across the fabric, and programmability within the network itself. The three components that built the Quantum 2 infrastructure, on the left side is the switch. Sorry for I forgot to do that one. On the left side is the quantum switch. So it's a 64 ports of 400 gigabit per second, and each port can be split to 2 ports of 200 gigabit per second to a radix of 128 ports of 200 gigabit per second in a single ASIC. That's an increase of 3x on the throughput with the number of ports here, which is probably the looking on an HPC switch. An HPC switch is probably the highest radix you can have there, and that with that you can build an infrastructure of 1 million endpoints with just 3 hops in that sense. New elements within the switches include increasing the ability of doing data reductions on the network to support multiple AI applications sharing the same infrastructure, and each one of those applications can leverage from running data reductions on the network. The ConnectX-7, the network adapter, 400 gigabit per second, PCI Gen 5, doubling the message rate, doubling the throughput on GPU Direct RDMA. Latencies on InfiniBand, if that's of an interest around GPU Direct RDMA, it's sub 2 microsecond, closer to 1.5 microsecond. Introducing new in-network computing engines. ConnectX-7 introduced an all-to-all engine in hardware. An engine that will increase all-to-all performance in a 4x to 5x comparison of running all-to-all operations from the CPU. Last and not least, on the right side, that's the Bluefield data processing unit. Bluefield is an important device as part of enabling capabilities for cloud-native supercomputing. Bluefield is a device that includes the ConnectX-7 inside. So it brings the full NIC functionality or the full network adapter functionality, adding multiple ARM cores, 16 ARM cores of ARM A78, a data path accelerator separate to the ARM core. So there's another 16 cores that sits on the data path, and infrastructure engines, engines for encryptions, decryptions of data, compressions, for example, other storage accelerations, network managements, and so forth. And those are the building blocks that enable us to build cloud-native supercomputing. On the switch element, bringing AI or reduction operation for multi-tenancy, as well as enabling performance isolation. Performance isolation, it's actually a combination of both the switch and the network adapter. And with the DPU, the ability to migrate the infrastructure workload, the data center operating system, the provisioning of the systems, the isolations between users, for example, and so forth, and actually run them on a new device. So instead of loading the CPU with non-application work, we can migrate the infrastructure workload into the DPU, and with that also increase the isolation between the application domain and the infrastructure domain. So one of the advantages of InfiniBand is essentially to provide a combination of networking services on one side and in-network computing services on the other side. On the networking side, InfiniBand was the first one to do 400 gigabit per second end-to-end, extremely low latency. The switches are doing sub 200 nanosecond for 64 ports of 400 gigabit per second. Very high message rate. I think that InfiniBand is probably the only network maybe out there that combines a full transport offload and native hardware RDMA. So then moving data directly to the host memory, GPU memory, to the storage from storage to the GPU memory, and so forth. All the elements of fine-grained adaptive routing, ability to build different kind of topologies, and so forth. On the other side, the in-network computing engines enables to migrate more of the sophisticated communication frameworks or communication operations into the network. Doing data reductions in hardware on the switch network enabled to reduce data motion by 2x, and to run the reduction operations much faster versus doing that on a CPU and maintaining same latencies regardless of the system size. Tag matching enables to not just reduce CPU overhead, but also to do to migrate rendezvous, the full rendezvous protocol, and to be executed on the network itself. And then with the NDR generation, also bringing an all-to-all engine in hardware. So enabling 4 to 5x performance increase on all-to-all operations. There is programmability with the, as I mentioned before, the data processing, the DPUs, the ARM cores, or the data path accelerator, and multiple engines around storage and around security and around isolations that sits around the data path accelerator and the ARM cores. So two elements that are new and important to enable cloud native supercomputing. The first one is performance isolation. And this is an example of testing that we have done and sharing with you the results. Here, what we did is we had or got access, have an access to a supercomputer. And at the beginning, we just pick one application. We pick LAMMPS, a molecular dynamic code. You can choose any other application, by the way. And what we did here is that we ran LAMMPS as a single application on the system and actually did it over and over again. And then plot an histogram that looks on the results. And as you see, as the single application running on the infrastructure, every time we run LAMMPS, we actually got the same performance. So that's represented here in a flat histogram. Next, we added more workloads around that. So it wasn't just LAMPS. Now we had workloads that were more storage oriented, workloads that were more all-to-all oriented, but different kind of workloads around scientific computing and AI elements. And we run LAMPS again, but now LAMPS is running in the presence of other workloads. And what's happening is that other workloads running on the same shared environment can impact our own application runtime. So sometimes we got nice performance results, sometimes we got half of the performance results, but as you can see, it's a very spread histogram. We don't get deterministic performance in this case, which is it's not a good thing when you want to bring more users to a shared environment. On the right side, this is where we enabled performance isolation. The ability of the network to control injection rates into the network based on telemetry information, based on round trip measurements, based on understanding needs of moving data. For example, when you get read operations, you actually know that you need to bring a lot of data through the network. So you can actually control the speed of the data to what endpoints can handle on one side, but to make sure that you don't create issues or interference within the network itself. So when enabling the performance isolation on the network, essentially we're getting very similar results for LAMPS running on a shared environment in the presence of other workloads, comparing to when LAMPS was just a single application on the system. Now we took the capabilities here and actually did a preview on Azure. So on Azure, we took 400 nodes on Azure, and we did the same experiment again. Here we chose 3 different applications. We took LAMPS again, a CFD code, in-compact 3D, and we took VASP, a quantum mechanical code. And in the first set of testing, we actually run each of those applications by itself. No other workload sharing the same Azure system here, and we plot the histograms, and you can see more or less we're getting very similar results running the same application over and over again in an empty environment. In the middle, you can see the results when we're running these applications, but in the presence of other workloads in the background. And the same as what we saw before. Now we're getting spread histogram, so we can get half of the performance. It even can be a 5x worse. Depends on what other things are running in the background. And then with enabling performance isolation, The dashed line, by the way, it's representing the performance of running the application just by itself. And the green one is the performance of the application running with the performance isolation enabled on the network. And now you can see the performance is very, very similar. In some cases, we're actually be able to overcome congestion. The application can create for itself and got a very nice histogram. And that's demonstrate that with performance isolation, you can actually host more applications on the network or on a shared environment without having one application impact another. For people that may ask, performance isolation here was enabled and all the applications were sharing the same virtual lane. So it's not a separate virtual lanes that isolate applications completely, but all applications were running on the same virtual lane. So this is one important capabilities with the Quantum 2 generation, where it enables to bring more users, more tenants, more applications on a shared environment, and making sure that one application will not impact another one. The DPU, going back to the DPU, going back to Bluefield. Bluefield brings great new capabilities to supercomputing. And on the right side, you can see a diagram of Bluefield just to get better understanding of the internal architecture of that. So Bluefield includes the ConnectX inside. This picture, by the way, it's Bluefield 2, and Bluefield 2 includes ConnectX 6. Bluefield 3 includes ConnectX 7, and so forth. So in Bluefield 2, you can see ConnectX 6, the multiple ARM cores, the different acceleration engines. The data path accelerator is not seen here, but there is also a data path accelerator. Memory interface, in Bluefield 2, it's DDR4, in Bluefield 3, it's DDR5. So there is memory on the card as well, and a PCI Express switch. Essentially, it's a full data center on a chip. So it brings the full NIC functionality, the full RDMA NIC functionality, but also there is programmability here with acceleration engines next to that. The PCI Express switch here enabled to connect other PCI Express devices directly to the DPU, directly to Bluefield. For example, flash devices, for example, GPU. And that's what we are doing with the H100C Next that was announced at the GTC recently, where we have cards with ConnectX 7 and Hopper that sits behind that. So that's enabled to connect GPUs or any other PCI Express devices. Bluefield goes to multiple areas. Edge computing is one example. And within the data center, it brings us three new capabilities. First capabilities is moving the infrastructure workload, the management of the data center, the isolations between users, for example, security, ability to provision servers if we want to provision servers, and do it completely from the DPU or from Bluefield instead of doing that on a CPU. Instead of creating an overhead on the CPU, and instead of mixing application domain and infrastructure domain on the same device. The other part is storage. The other part is storage. And with Bluefield, we able to actually enable computational storage infrastructures, a solution based on computational storage. Bringing the abilities to do compressions and decompressions and encryptions capabilities and checksums. Enabling actually the DPU to be device where the user application is going to mount storage on top of the DPU instead of the need to mount storage on the real storage, and then the DPU actually is a device that mounts storage on the storage. That's enabled to reduce jitter, for example, because of this the storage activities done on the CPU and other things, so reducing other overheads that exist from that perspective. The third one is enabled to migrate more of communication frameworks and actually do that on the network. So those are the three elements. The first two I mentioned. If we want to isolate between users, we can, and use the DPU instead of doing that on a CPU. We can bring zero trust architecture or zero trust capabilities into supercomputing by actually keeping the user within the server. It could be even a single user, but the user stays within the servers, and then everything that happens outside of the server actually controlled by the DPU. And that enable us the ability of multi-tenancy, of course, more users, SLAs, and so forth. The other part that I mentioned is using Bluefield to accelerate communication frameworks, and you can do multiple things with that. The DPU or Bluefield, it's a device that can do native RDMA operations, native RDMA operations locally, native RDMA remotely. It can do manipulations on the host memory without the need to copy data from the host memory, and so forth. So you can leverage Bluefield, for example, moving collective operations to be done on the DPU. So on the InfiniBand network, for example, we do have reduction operations already running on the switch in hardware. And Nickel, just as an example, already incorporated Sharp or the data reduction in the network within Nickel. And that enables us to actually take MLPerf applications and improve them by 20 to 30%. With combining the data reductions on the network with Nika, for example. But you can use the DPU for other collective operations, gather operations, all-to-all operations, and so forth. You can use the DPU for active messages, for MPI progression, for, as I mentioned before, computational storage, or any other user-defined algorithm. To move algorithms to the DPU and run them closer to where the data is, and leverage the hardware engines. It's leveraging the in-network computing that we have within the DPU and within the InfiniBand network. So the combination of that, it's actually very, very powerful. DK presented in the first day some of the work being done with Mvapich on the DPUs, and I do have a couple of slides here just as a recap on different colors. But moving non-blocking MPI operations on non-blocking MPI collective operations from the host to run on Bluefield enable in average to reduce the total time by half. There is 30-something% for all-to-all. There is 50% on all gather. There is more than 50% on broadcast, for example. So there is a nice ability to reduce the time for non-blocking collective operations. And by moving those operations to Bluefield, you actually can achieve overlapping. And I think Vicky also presented the overlapping capabilities, actually moving from almost 0% overlapping to 100% overlapping. By leveraging the DPU, not just as moving the a non-blocking MPI operation, but also to leverage the hardware engines there that make it very, very effective. Then in return, it can bring nice boost to different kind of algorithms or applications. And one example is the three-dimensional FFT. As mentioned probably by DK again, the three-dimensional FFT was based on all-to-all operations. So it was modified in the combined effort to move from blocking all-to-all operations to non-blocking all-to-all operations. And by moving to non-blocking all-to-all operations, now you can leverage the DPU to actually run MPI in parallel of progressing compute on the CPU, and that gave 1.2, 1.3x performance improvement to FFTs. Another example is mini-MD. So it's a mini applications, mini molecular dynamic applications. And this is a shared effort between Georgia Tech and Sandia National Lab that we were happy to host and have them present that in recent GTC. And what they did here, it's actually took part of the algorithms of mini-MD and actually migrate that to the DPU. Run it in parallel and leverage the ability to run such data algorithms much closer to the data. And that's being done on the DPU. The result was increase of almost 20%. Increase of almost 20% in application runtime because of leverage the DPU. So it's two nice examples of where having an engine that includes all of the NIC functionality, the right hardware engines, extremely low latency of the network, obviously, to be able to host more elements from communication frameworks and able to do overlapping between compute and communication, and results in 20 to 30% performance improvement for different kind of workloads. Now it doesn't stay also only there, but the DPU, it's also an element that can enable to bring predictive maintenance, for example, as well as more security into supercomputing infrastructures. DPU is an active element, can collect telemetry information, not from the network, but also from the host itself. So instead of getting the CPU busy with collecting telemetry information or the GPU, the DPU can actually do that and send information, send telemetry information to a GPU, and that's what we do today on with the Morpheus framework, the data center security framework. Morpheus framework runs on a GPU and gets telemetry information from the network and from the DPUs that collect information that's coming from the server. Morpheus is trained to look for sensitive information, for example, to identify usernames, passwords, sending the open, to identify anomalies in the usage of the data center and so forth. And when detecting anomalies, to provide alerts. When detecting sensitive information, sending the open, to actually alert Bluefield to shut down the server that actually the data is being leaked out. So it's not just bringing a ability of increased application performance or enable to migrate the infrastructure workload out of the CPU, have the CPU be dedicated to the application and run it on the network, but also bringing capabilities of anomaly detection and security and other things, which will become very important as supercomputing infrastructure will host more users and more applications. In order to utilize the DPU in a very easy way, and to ensure that any workload, any application written on Bluefield from one generation will carry to the next generation and so forth, we built a software development kit and runtime called Doka. Doka for the DPUs is very similar to CUDA running on the GPUs. Doka exposed the capabilities of Bluefield, the networking services, the storage services, telemetry services, the security, all the acceleration engines, the data path accelerator, the ability to program the data path accelerator and the other engines, expose that to applications running on top. It could be the infrastructure application when we're looking on a shared environment. It could be to scientific computing applications, AI applications, and so forth. And those applications can utilize the elements on the DPU in a very easy way. There is a link here, by the way, to Doka if someone wants to get more information about the interfaces and how to utilize the DPU. So with that, I think I'm on 30 minutes time, so giving also back 10 minutes. Thank you very much for listening.
Cool. Thank you very much. Enjoyed the talk. Are there any questions or comments or discussion on that anyone would like to type into the chat or raise their hands for verbally discussing? Okay, I have nothing in the chat. So thank you very much.
Thank you.